If a natural disaster severed the massive interconnected global pipeline grid tomorrow, you probably think modern civilization would just go completely dark.
Right. Yeah, people assume everything just stops.
Exactly. But behind the scenes, operating totally silently under the radar, you have hospitals, heavy industry, entire cities just being kept alive by this heavy, invisible gas that behaves, well, almost exactly like water.
It really is the ultimate invisible lifeline.
Yeah. And today, we are taking a deep dive into the shape-shifting marvel of liquefied hydrocarbon gases, specifically propane-butane mixtures.
Better known to most people as LPG.
Right. And okay, let's unpack this because our mission today is to demystify this fuel. We're pulling from a really detailed technical engineering lecture about autonomous and backup gas supply systems just to figure out why its global use is surging so fast.
Yeah, and we'll dig into the surprisingly unforgiving physics of how it actually works. Because, most people only interact with LPG when they swap out that little white tank for a summer barbecue.
Oh, yeah, or like twisting one of those tiny green cylinders onto a camping stove.
Exactly. You just see it as a weekend accessory. Right. But on a global scale, it is a massive driver of the economy. It's a highly technical engineering marvel.
So to really grasp the importance of this, we need to look at the sheer scale of the growth. And the data in our source shows this staggering leap.
What's fascinating here is just the window between 1995 and 2005 alone.
Right. It jumped from like 150 million tons to 210 million tons globally.
Yeah, that is a 40% increase in just a single decade.
Which is insane. But a surge like that doesn't happen evenly everywhere, right? The source points out that the Asia-Pacific region is really the primary engine driving all that demand.
Which tracks perfectly. I mean, considering their rapid economic development, industrialization, and just massive populations transitioning to higher energy needs.
Totally. And to feed an appetite that large, you have to look at who is actually exporting this stuff.
Right. And Qatar is at the absolute top of that list. They handle roughly 22% of global exports.
Wow. 22%.
Yeah, and Australia follows super closely at 21%, and then you've got the USA at 10% and Russia at 8%.
See, when you lay out those numbers and you think about how this fuel moves from Qatar to the Asia Pacific or like from Australia to Europe, I kind of start to visualize LPG as the ultimate liquid currency of energy.
Liquid currency, I like that.
Well, think about natural gas, right?
Yeah.
It's physically tethered to the ground. You need these multi-billion-dollar, totally fixed pipeline networks.
Very rigid infrastructure, yeah.
Exactly. But LPG is completely geographically untethered. You load it onto ships, you put it on rail cars, you can literally drive it across a desert in a standard truck.
And that untethered mobility is purely down to the physics of its phase transition. LPG is, well, it's a shapeshifter.
A shapeshifter.
Yeah. At normal atmospheric conditions, like the temperature and pressure you and I are sitting in right now, it's a gas. But if you apply relatively mild pressure, it transitions instantly into a liquid.
And that is the secret sauce right there.
Right. You don't need to cryogenically freeze it to hundreds of degrees below zero like you do with liquefied natural gas.
You just squeeze it a little bit.
Just a mild mechanical squeeze. And that condenses the molecules beautifully. By shifting it into a liquid, you increase its density by hundreds of times.
So you're packing this massive, dense volume of energy into a super small, transportable steel container.
Exactly. Then when it reaches the end user, you simply release that pressure, and it essentially boils back into a highly controllable gas.
Okay, so it's incredibly portable, it's heavily traded. But if it requires all this specialized shipping from places like Qatar or Australia, who is actually buying all of it? Like, what justifies that global logistical effort?
So the engineering documents actually break global consumption down into 4 main pillars.
Okay, what's the first one?
The vast majority, so a full 50% of the global pie goes to the communal and domestic sector.
Wow, half of it.
Yeah, half. That means heating homes, cooking food, heating water in rural areas where laying a traditional pipeline just isn't feasible.
So half of it is just for daily human survival. That's wild. What's the second pillar?
The petrochemical sector, which takes up about 22%.
Okay, and it's staggering to realize that nearly a quarter of this fuel never actually gets burned.
Right. It's used as a raw material, a chemical building block.
Right. The propane and butane molecules are physically rearranged to synthesize things, like plastics, synthetic rubbers, pharmaceutical precursors.
Exactly. The phone you are holding in your hand right now, or the dashboard of your car, it very likely started out as LPG.
That's crazy to think about. Okay, so that's communal and petrochemical. What are the last two?
The third pillar is transport, specifically auto gas, which is expanding really rapidly globally. And that leaves the fourth pillar, which is industrial use. Currently, heavy industry only accounts for about 12.5% of global LPG consumption.
Okay, wait, let me push back on that industrial number for a second,
Okay.
because the source documents make a huge point of emphasizing how energy efficient LPG is.
It is very efficient, yeah.
Right, it has a massive calorific value, meaning it packs a ton of heat per unit, and it burns exceptionally clean compared to other fuels. So if it's this clean, high-performance powerhouse, 12.5% seems strangely low to me. Why aren't massive factories just running on this stuff all the time?
Well, it comes down to the brutal math of industrial economics.
Money.
Always money. LPG is a highly refined premium product. So if a massive steel mill or, say, a glass factory is looking at their daily operating costs for continuous large-scale heating, LPG is simply too expensive compared to the alternatives.
Oh, so they just default to standard pipe natural gas.
Natural gas, or even cheaper, dirtier fuels like diesel or mazout.
Mazout. I've seen that mentioned before in industrial contexts. That's essentially that thick, tar-like, heavy fuel oil left over at the very bottom of the barrel after refining, right?
Yeah, exactly. It's the bottom of the barrel sludge.
It's super cheap, but it burns incredibly dirty.
Very dirty, but very cheap, which makes it super financially attractive for heavy industry. However, our source points out a highly counterintuitive trend happening right now in Ukraine.
Oh.
Yeah. Despite the premium cost of LPG, industrial consumption there is actually growing by at least 5% annually.
Huh. But if it's too expensive to burn continuously, they must be using it as an insurance policy.
You hit the nail on the head.
I mean, the cost of a factory suddenly losing its natural gas supply, like machines seizing up, production lines halting, raw materials being ruined, that financial loss has to be drastically higher than the premium price of keeping a massive LPG tank on standby.
That is the exact calculation they are making.
Yeah.
Industries are utilizing LPG as a dedicated, autonomous backup fuel. When the grid fails, the LPG system instantly takes over to keep the plant alive.
But to function as a flawless insurance policy like that, something that can instantly power a massive industrial facility without any warning, it can't just be any random gas pumped into a steel cylinder.
No, absolutely not. The engineering has to be bulletproof.
Right, and here's where it gets really interesting, because we need to look inside the tank at the microscopic chemical level. The fuel itself is highly engineered.
It's a very strict chemical balancing act. LTG primarily originates from two sources, actually.
Okay, which are?
It's either extracted alongside natural gas and crude oil straight from the earth, or it's a secondary byproduct created during the oil refining process.
And I'd imagine the chemical makeup changes depending on where it comes from.
Drastically. The foundational components of LPG are a group of saturated hydrocarbons called alkanes, specifically propane and butane.
Those are the two names everyone recognizes.
Right. And they're saturated, which means every carbon atom holds the absolute maximum number of hydrogen atoms possible. They're very stable.
But if the LPG comes out of an oil refinery, it brings along some microscopic hitchhikers.
Right. Yes, it does. The refining process introduces unsaturated hydrocarbons, which are called alkanes, things like propylene and butylene.
Okay, and because they are unsaturated, they have a double bond between carbon atoms.
Exactly. And that double bond alters how they behave under pressure, which is where the engineers have to step in and enforce these incredibly strict vapor pressure rules. You cannot just mix these hydrocarbons randomly.
So think of the molecules inside a pressurized tank like, I don't know, people trapped in a closed room. The source says you absolutely cannot have too much ethane or methane in the mixture. Mechanically speaking, why is that a problem?
Because methane and ethane have very low boiling points. So, going back to your closed room analogy, they are the hyperactive children bouncing violently off the walls.
Okay, I can picture that.
They vaporize furiously, and that causes the vapor pressure inside the steel tank to spike to dangerous, structurally threatening levels.
Too many light molecules, and the tank is under extreme stress. But the flip side is also true, right? The source states you cannot have too much pentane in the mix either. And pentane is a heavier molecule. So if methane is the hyperactive kid, pentane is, what, a sluggish adult refusing to get off the couch?
That's a perfect way to put it. If the pentane levels are too high, the vapor pressure drops way too low, the gas becomes completely lethargic.
So it won't vaporize fast enough.
Right. It physically won't flow through the pipes to reach the burner, especially if the outside temperature drops.
Before we move off the chemistry, I noticed the document also mentions strictly limiting pentane, quote, and its isomers.
Yes, isomers are crucial here.
Just to clarify for anyone listening, an isomer means you have the exact same chemical formula, like the same number of carbon and hydrogen atoms, but they're physically assembled in a different structural shape.
Like taking a Lego house and rebuilding it into a Lego car?
Exactly. But why does the physical shape of the microscopic molecule matter to the gas flowing through a pipe?
Because the physical shape dictates how closely those molecules can pack together, and that directly changes their boiling point.
Oh, wow.
Yeah. A straight-chain pentane molecule boils at a different temperature than a branched pentane isomer. So in a system that relies entirely on precise vapor pressure to push gas through a pipe, even a slight shift in the boiling point changes the entire fluid dynamic.
That level of precision is incredible. And these aren't just like polite industry suggestions, are they?
Oh no. These chemical limits are governed by hyper-specific, strict national engineering codes to guarantee the fuel behaves exactly as expected.
Okay, so beyond the chemical makeup, the physical properties of LPG demand massive respect from the engineers designing the infrastructure.
Absolutely. First, you have the weight.
Right, because unlike standard piped natural gas, which is lighter than air and will just float up into the atmosphere if there's a leak, LPG vapor is significantly heavier than air.
Which is a huge safety consideration.
Meaning if a pipe bursts in a basement or, say, an industrial trench, the gas doesn't dissipate, it sinks.
It behaves almost like a liquid water spill. It finds the lowest possible point and pools there invisibly, just waiting for an ignition source.
That's terrifying.
It is. And that pooling factor dictates entirely how storage facilities and ventilation systems have to be architected. But the second physical constraint is actually even more volatile.
Liquid expansion.
Yes. The source explicitly warns that liquid LPG has a massive volumetric expansion coefficient when warmed.
It expands far more aggressively than water or gasoline or kerosene.
Way more.
And liquids, by the basic laws of physics, are essentially incompressible. You cannot squeeze a liquid into a smaller space.
Because of that incompressibility, there's a hard, unbreakable rule in the LPG industry. A storage tank can never, ever be filled to more than 85 to 90% of its geometric volume.
You absolutely have to leave an empty vapor space at the top.
Always.
Let's play out a scenario. Let's say someone ignores the rule. They fill a cylinder completely to 100% with cold liquid LPG on a freezing winter morning. What happens?
Well, when the afternoon sun hits that steel tank, the liquid inside warms up and attempts to expand. But because it takes up 100% of the space and the liquid cannot be compressed, that thermal expansion translates instantly into massive, catastrophic hydraulic pressure against the internal steel walls.
So you just explode.
The tank will literally tear itself apart from the inside.
Wow.
Yeah.
Okay, which brings us to the actual logistics of moving this stuff. We have a heavy gas that pools, a liquid that acts as a hydraulic bomb if overfilled, and a mixture requiring perfect vapor pressure.
It's a lot to manage, yeah.
How do engineers actually move this safely from a massive regional storage base to a factory burner?
It's a highly tiered logistical chain. The bulk transport relies on specialized railway tank cars that move the liquid across the country to regional distribution bases.
Okay, and from the base.
From there, specialized tanker trucks deliver it to the specific end-user sites.
And at the site itself, the engineering categorizes the setups by size. You have individual installations, which are small-scale setups using just 1 or 2 cylinders for maybe a rural home.
Right.
But then you have group setups, which utilize multiple cylinders or massive bulk tanks installed either underground or above ground for large facilities.
And for those massive industrial group setups, there's a fascinating piece of technology mentioned in the source, the mixing unit.
Okay, what does a mixing unit do?
Some facilities do not burn pure LPG vapor. They utilize automated mixing units to physically blend the LPG with atmospheric air before sending it into the facility's pipe network.
Wait. Pre-mixing fuel and oxygen inside an enclosed pipe. That sounds like you were just building a bomb.
Right.
You are literally giving the fuel exactly what it needs to ignite before it even reaches the burner.
It seems entirely counterintuitive to safety. I agree.
So why do it?
Well, the purpose of the mixing unit is often to dilute the LPG, so its burning characteristics perfectly mimic standard natural gas. That allows a factory to instantly switch between the two without changing out all their expensive burner nozzles.
Okay, but how do they do that safely?
The automated engineering relies on a concept called the upper flammability limit.
Okay, let's break that limit down for you listening. For combustion to happen, you need a specific ratio of fuel molecules to oxygen molecules. If there's too much air and not enough fuel, It's too lean to burn.
Exactly. But the mixing unit operates on the complete opposite extreme. The engineering standard dictates the mixture inside the pipe must be kept at a concentration that is at least twice the upper flammability limit.
Oh, so it is entirely too rich to burn.
Exactly. You are crowding the pipe with so many hydrocarbon molecules that there simply isn't enough oxygen present between them to allow a flame to propagate.
So even if a spark went off inside the pipe, it physically could not ignite.
Nope. It only becomes flammable once it exits the burner nozzle and mixes with the ambient air in the room.
The safety margins are literally baked right into the chemistry.
They have to be. And to ensure that rich ratio never drops into the danger zone, the mixing units are loaded with automated sensors.
I'd imagine.
If the concentration even begins to drift toward flammability, or if a single compressor fails, the system instantly and automatically shuts the entire operation down.
That is failsafe engineering at its finest. Okay, now, here is a mechanical question. Let's look at a factory using this as a backup.
Okay.
The power grid drops, and a massive industrial furnace suddenly demands a tremendous volume of gas instantly.
Right.
But the LPG is sitting outside in a massive tank as a liquid, just letting it sit there, relying on the ambient heat of the outside air to slowly boil the liquid into a gas that cannot possibly be fast enough to feed an industrial furnace.
No, natural evaporation completely fails at an industrial scale. The thermodynamic reality is that boiling requires heat.
Right.
As the liquid LPG boils off into vapor to feed the factory, it rapidly absorbs heat from its surroundings.
So it basically refrigerates itself.
Exactly. The remaining liquid gets colder and colder, which drops the vapor pressure until the liquid becomes so cold it basically stops boiling altogether.
And the factory starves.
Right. So to solve the freezing problem, engineers integrate artificial heat using specialized devices called evaporators or vaporizers.
And the source documents highlight two highly effective designs for this.
Yeah, the first is the flow-through evaporator.
Okay, so in a flow-through system, you pull the liquid out of the main storage tank and pump it through an external heat exchanger. You're boiling it outside the main tank.
Right. And the brilliance of the flow-through design isn't just speed, it actually solves a hidden chemical problem called fractional distillation.
Fractional distillation. Walk us through that.
Well, remember how LPG is a mix of propane and butane?
Yes.
Propane boils at roughly negative 42 degrees Celsius. Butane boils much warmer at roughly negative half a degree Celsius.
So if you just apply heat to the bottom of a giant mixed tank, the lighter propane is going to boil off first and travel into the factory.
Exactly, leaving a giant puddle of sluggish, heavy butane behind in the tank.
Which means you are constantly changing the chemical mixture the factory receives over time.
Right, which ruins efficiency. But in a flow-through evaporator, you extract a small, steady stream of the mixed liquid and flash boil it entirely inside the external heat exchanger.
Because you are instantly vaporizing the entire sample all at once, the gas delivered to the factory retains the exact original proportion of propane and butane.
Exactly. The composition never fluctuates. It is a highly consistent feed.
Okay, so that's flow-through. The source also mentions a second type, the capacitive evaporator.
The capacitive design takes the complete opposite approach. Instead of pulling the liquid out to heat it, specialized heaters are built directly inside the main storage tank itself.
So it actively heats the bulk liquid internally.
Yeah, it forces the evaporation rate and maintains the required pressure inside the tank no matter how cold the outside environment gets.
Wow. We have really journeyed from macro global economics and massive 40% growth trends all the way down to the molecular shape of a pentane isomer and into the internal heating elements of a steel backup tank.
It's a lot of layers to unpack.
So what does this all mean? When you synthesize all this engineering data, the picture that emerges for you listening is that LPG is infinitely more than just a camping commodity.
Oh, absolutely.
It is a highly refined chemical tool. It's a foundational block for global manufacturing and an increasingly critical safety net keeping our industries alive.
And honestly, analyzing the resilience of this fuel leads to a very provocative thought about the future of our energy infrastructure as a whole.
How so?
Well, we started this deep dive talking about the rigid, fixed nature of traditional pipeline grids.
Right, tethered to the ground.
But as extreme weather events escalate and complex geopolitical conflicts increasingly target or disrupt those fixed pipelines, the grid is proving to be incredibly fragile.
Because you cannot easily reroute a severed underground pipeline.
Exactly. But you can reroute a fleet of trucks carrying a liquid that expands into a massive volume of gas.
Huh.
We might actually be witnessing the early stages of a paradigm shift right now. With its highly mobile, geographically untethered nature and all the advanced failsafe engineering we've discussed, LPG might transition from simply being an emergency backup for when the grid fails.
To becoming the foundational blueprint for a completely new, decentralized global energy network.
Exactly.
A system where the energy travels fluidly to exactly where it's needed, entirely independent of a fixed pipe in the ground, the ultimate liquid currency taking over the market.
It's definitely a powerful concept to ponder the next time you hear the familiar hiss of a tank opening.
You were listening to the sound of precision chemistry, fail-safe engineering, and quite possibly the future of our global energy resilience.